All right. Second part to this lab is creating the tug of war scenario. So the rope and the forces pulling on it. So you've got your paper clip that's going to act as kind of our central notch point. The big thing right now is this washer is actually going to go over this notch, and that's going to let you know who's winning the tug of war or if it's balanced. For instance, if it were kind of floating right in the middle, that would be balanced, which is the goal. We want equilibrium to achieve Newton's first law. If, though, a force were pulling maybe too hard to the right, you would see it pinned up against the paper clip, which is not what we want. That would be unbalanced, of course. So anyway, get a washer, and the first thing you're going to do is, of course, with these strings cut and the loop knot made on each end, you're going to feed one end through the paper clip here, or not paper clip, excuse me, the washer. And then what's cool about these loop knots is if you open that loop knot up and then feed the other end through it, it'll actually secure itself once you pull it through. And it's not actually creating a knot. You can then undo this and reuse the string later for future labs, so that's really nice. So what's the point of that? Well, now here's this end of rope that will play one team's tug of war, if you want to relate to that. How does it create a force? Well, the other end of this, you're then going to hang one of these paper clips. And of course, depending upon which part of the lab you're on with whatever amount of washers, you're going to then put some washers on this. And if you hang it over the side, this weight, gravitational force pulling down, will really then create a force of tension in this string, pulling the washer to the right, the positive x direction, or 0 degrees, if you're going to do the degrees around a circle. You can clearly then see, since that's the only force pulling to the right, this is unbalanced. So let's say that we're the only force. How do we then get it balanced? Well, that's where the spring, which we've already used, because this can tell us a force if we know the spring constant and how much it stretches, so be mindful you can measure that. We can then actually, with this washer, place it around the washer. And of course, if I don't pull, it's still unbalanced this way, but if I do pull, kind of thinking about it, well, that's pulling to the right, I've got to pull to the left. So I'm going to pull directly to the left, and of course the spring is stretching, and eventually at some force I'll see it balanced. Now if I pull it too hard, I'm going to then have it unbalanced the other way. My force is too much. So the goal is then to basically counter that force, and then once I have it balanced, well, if I measure this new length and find the displacement from the original length, and I know this spring constant, I can then, of course, find out, well, what force was needed to balance it, okay? Of course, you'll make your prediction before you do that. This then is how you check your prediction with how much it stretches multiplied by the spring constant. There's then another scenario, because that's pretty easy. That's just one dimension, all right, x component. What if actually we take the second half of that string that we made new loop knots with, feed it through, just like you did the first, take the other end and actually loop that through. What if we actually add another force? And this time I'm actually going to hang this one off of the other corner of the table. So take my paper clip that I haven't used yet, and again hang some amount of washers depending upon what part of the lab. This then, when I hang it over this part of the table, will create another force, but this direction. So you can see it's not just unbalanced to the right, it's actually unbalanced at an angle to the right and, let's say, down. All right, again, making predictions, you can do some math and Newton's first law to figure out, okay, what would need to be the third force to balance this out and get it unpinned. Once you do your prediction, then, like we did before, you can actually take this paper clip, hook it around, and try to then find, okay, what force do I need to pull with? Now this one's a little bit trickier. It's going to have a funny angle. It's not one dimension, it's two. So what we should be doing before this is actually, with your protractor, put the little hole part right over the paper clip. This will then help you measure exact angles. It can even check, before you go, if this is exactly at 0 on the right side, and then this is perfectly 90 degrees with it. So if I am trying to achieve 90 degrees, I probably should check with this. Then when I actually, trying to keep my arms out of the way, when I hang this, I could actually flip this protractor around, again making sure it's still on 0 over here, and then I could have an exact angle over here. So I can measure the new displacement, the new length, getting a new displacement, and then of course an angle as well. So I will say one thing, if you do not have a hole on your protractor, I can't remember if they all do, you can of course untape this, put the protractor down first, and then just tape this right on top, but make sure the notch part is right on top of where that little circle would be, where the X kind of marks your starting point. All right, so hope that helps. Again, the idea is tug of war. We want it to be balanced. So you're trying to make the predictions with Newton's law to figure out what would be that final force to balance it, and then you can check it with your spring based on its amount of stretch and the spring constant you've learned before. All right, guys, hope that helped. Good luck on this.